So last time we were discussing about sound as an example of longitudinal mechanical waves. We saw that the equation of a one-dimensional harmonic sound wave is given by two phenomena: displacement as a function of position and time, as some sort of amplitude into a harmonic function. Okay, so this is a sound wave propagating along the x-axis. At a propagation speed of omega by k, which is equal to f lambda. Rather, 2 pi by k. And s represents the longitudinal displacement of a medium particle at x equal to x at time t equal to t. Now we saw that this is also accompanied by a pressure variation, or what we call a pressure wave, which is then represented by an equation like this, where this quantity represents the pressure change, or what we can call volume stress at a point x equal to x at time t. So the relationship between these two we had seen is that the pressure amplitude is given by beta into k into s naught, where beta is the Bulk's modulus of elasticity. Okay, so this is a quick recap of what we had learned in the previous lecture. Just go through this. We'll discuss some more things here also. Right. So in this, now the next important thing we've seen is that the propagation speed is a medium, is dependent on the medium's physical properties. Okay. So this V, which is equal to f lambda, in this the V is given by square root of Bulk's modulus by density for fluid media, and is given by square root of Young's modulus by density for solid media. Okay. Now in this also, when we discuss about sound waves propagating through ideal gases, okay, so speed of sound and audible sound has a frequency range of 20 to 20,000 hertz. So through an ideal gas, okay, we're talking about, so this frequency range is such that we can observe that what is typically happening is that the propagation of sound involves very fast compressions and rarefactions. Okay, and as you have will learn in heat and thermodynamics very soon, fast compressions and rarefactions can be approximated as adiabatic processes. So the propagation of sound thermodynamically involves the medium of the ideal gas undergoing an adiabatic process. So adiabatic process is given by the relation PV to the power gamma is constant, where gamma is ratio of Cp by Cv, or 1 plus 2 upon degrees of freedom. So you should remember that gamma is equal to 5 by 3 for monoatomic gases, and it is equal to 7 by 5 for diatomic gases. You might have done this in chemistry so far, right?
Yes.
And physics, I think you're just reaching
we
this
did
point.
It in chemistry. Yes.
Yeah.
Physics.
Physics also, you have done kinetic theory of gases already, I think. Right?
Yes, sir.
So in that you would have seen the degrees of freedom and
yes.
Okay, so yeah, and for polyatomic gases, yeah, gamma is 3 in certain cases, but in certain cases it can be different because degrees of freedom can also have more than 6. It can have vibrational degrees of freedom also. Okay, so it all depends on the exact gas molecule you're talking about. Whereas certain polyatomic gas molecules can also be linear, like diatomic molecules, like sulfur dioxide, for example. Sulfur dioxide, or even carbon dioxide for that matter, it has a structure like this. So it is more or less a linear structure. So it more or less behaves like linear material, like diatomic. But then at higher temperature, vibrational degrees of freedom also come into play. So that's why we don't have one fixed formula for polyatomic gases. But for diatomic and monoatomic gases, we have one fixed value or one fixed set of formulae for Cp, Cv and all this. Okay, which is something that you should keep in mind. Okay, now coming back to this, so adiabatic process is given by this relation. Now in this process, what happens is when we define the bulk's modulus, okay, it is nothing but mod of dp divided by dv by v, because it is nothing but volume stress. That is the change in pressure, which is dp, divided by volume strain, okay, which is the fractional change in volume. So for an adiabatic process, what happens is that when we apply this formula, you see that we get something called adiabatic. In general, this is bulk's modulus definition. Okay. But for an adiabatic process, it becomes defined as PV to the power gamma is constant. So if we differentiate this, it means that dP into V to the power gamma, that is derivative of first into second, plus P into derivative of second, which is gamma V to the power gamma minus 1 dV, is equal to 0. So from this we get the relation that if you take V to the power gamma minus 1 common, you have V dP plus gamma P dV is equal to 0, which further tells us that dP divided by dV by V, if you just work this out by, okay, or wait, one step before that. So the step before that is that this term in the bracket should be 0, because volume can obviously not be 0. So V dP is plus gamma p dV is equal to 0. So this further implies that V dP is equal to minus gamma p dV. From this we can see that dP divided by dV by V is equal to minus gamma p. So now from this we can understand that the bulk's modulus is going to be mod of this dP divided by dV by V becomes gamma p for adiabatic process. Hence this is also called the adiabatic bulk's modulus. Okay, so therefore the speed of sound, which is square root of beta by rho, becomes square root of gamma p by rho, and then you use the ideal gas equation. PV equal to nRT also means that pressure into molecular mass is equal to rho RT, where rho is density. So using this relation, we come to another formula. So the formula is the important thing for us here, that because it is an adiabatic process, it's bulk's modulus by density, but it can also be expressed as square root of gamma RT divided by m. So this becomes the ultimate formula for speed of sound propagating through an ideal gas. And this formula theoretically gives us the correct value of speed of sound through atmospheric air at room temperature compared to the measured value experimentally. So it is accepted as the successful hypothesis which agrees with the experimental value. So you can definitely get simple formula based questions compared to this. For example, if speed of sound through, let's say, hydrogen at a temperature T is, let's say, 680 meters per second, then find the speed of sound through, let's say, through helium at 2T. But this 2T is in kelvins. Okay. This is also in kelvins. So you have to just do a simple comparison of these two, not even the application of the formula. So let's say this is V2 and this is V1. So from the formula, you can see V1 by V2 will be square root of gamma 1 by gamma 2 into M2 by M1 into T1 by T2. Okay. So 680 divided by this unknown speed V2 will become, now helium is what type of gas? It's a monoatomic gas. Yes, that's correct. Very good. So helium is a monoatomic gas. Okay. And its molar mass is 4 grams, 2He4. Okay. Whereas hydrogen is a diatomic gas. Okay. And its molar mass is 2 grams, H2. Okay. So this will become 7 by 5 divided by 5 by 3 into 2 by 4, okay, into T by 2T. So 680 by V2 is coming out to be square root of 21 by 100. This is what I'm getting. So from this you can find out whatever V2 is. Also, if you're doing a direct question, you have to be very careful about substituting values. So for example, speed of sound through oxygen at 27 degrees C. So when you substitute in the formula, just make sure to take everything in SI unit. Gamma will be equal to 7 by 5 because it's okay. Now M, it is 32 grams. So you will substitute it as 32 into 10 raised by minus 3 kg. Okay. And temperature you will substitute as 300 Kelvin and R as 8.314 joules per mole Kelvin. On substituting all this, you will get the speed of sound correctly in meters per second. So just be careful when you are doing these kind of substitutions. It's very common mistakes to substitute molar mass in grams instead of kgs or something, and then come up with the wrong answer. So this will give us the value in meters per second. I'm not completing the calculation, it will take too much time. But just be alert about that when you're substituting all the units. Okay, so this is one special thing to remember about speed of sound. And this formula has a special name. It is called the Laplace correction, because a physicist called Laplace made a correction to the theoretical model of sound propagating through air. Previous to him, Newtonian physicists had predicted that the propagation of sound is an isothermal process. So they got a different formula for speed of sound. Okay, so I won't get into that whole thing here to save time. But for a long time in physics, the theoretical model of speed of sound did not agree with the experimental value. Till this was realized that no, it is not an isothermal process, even though the temperature of air is not so much affected by the speed sound propagating through it, but it's better approximated as an adiabatic process because the compressions and rarefactions are so fast that there is no time for heat exchange. Okay, so let's move on. Now, from speed of sound, we had also seen the concept of intensity of sound wave. So there also we have to discuss another aspect, that is intensity in decibel scale, which I'm sure you would have heard about. The term decibels, you must have come across it somewhere or the other.
Yes, sir.
So what does that mean, and actually how we do the calculation of decibels? Okay, so first of all, coming back to intensity of a sound wave in SI unit first. So what we mean by the term intensity is it is the energy propagated per unit area per unit time. okay, by a sound wave. So if we have a sound wave represented by this kind of equation, okay, or the corresponding pressure wave, which represents the same thing. Okay, just a moment. Okay, okay, sir. Yeah, people, sorry, I got disconnected. Probably I didn't realize. Yeah, so I think we are all clear up to this point, right? The definition of threshold of hearing and threshold of pain.
No, sir.
Achha, so I had gone offline then only. Sorry.
Yes.
I did not realize actually that somehow my net connection had got disconnected. And I
They
went for
disconnected right after the question.
after the question only.
Yes.
Oh, so this whole intensity thing. Okay, okay.
So,
Oh, so we were here, was it?
you explain Laplace correction and all that.
Laplace correction. Okay, so this is
Yes.
clear now. Okay, okay. Now next, I think we are talking about intensity of sound, and I told you that there's something called decibel scale that we are discussing. After that, I must have got disconnected, right?
Yes.
Okay. So intensity of sound, we saw this in the last lecture only. This is the formula for intensity. Okay, this one here. Okay. So according to this formula, now here you can also write V as square root of beta by rho. So it will reduce to this. Okay. But more importantly, you can see that because intensity is proportional to displacement amplitude square, so it is also proportional to pressure amplitude square. So these two relations are important, that proportionality of intensity with respect to amplitude, whether we are talking about the displacement amplitude or we are talking about the pressure amplitude, is the same. It is proportional to square of amplitude. Okay. Now next, having understood this, this is the thing I think where I got disconnected. This is the part. So audible sound. So what do we mean by audible sound? Sound that is audible to human beings. That means sound that is processed by our sensory nervous system as some kind of a signal which our brain interprets as, okay, we have heard some sound. Okay, so at the physical level, what is sound? It is nothing but a pressure wave propagating through the air. But at the neurosensory level, what it is, it's ultimately the processing of some kind of signal which our nervous system picks up from our ear, okay, and then converts into some kind of a message in our brain center which has to do with hearing. So for that whole process to happen, the sound has to have certain properties. So what are those properties? So there are properties in terms of two things. One is in terms of intensity or loudness, okay, because intensity more or less translates to loudness, and the other has to do with frequency. So for any sound to be audible to humans, the frequency has to be in this range between 20 and 20,000 hertz. Whereas for any sound to be audible in terms of loudness, because if the sound is too soft, then again it will not create enough disturbance for our eardrum to vibrate enough, and therefore there will be no signal that is being produced and sent to the brain. So there has to be a certain minimum loudness or a minimum intensity in terms of physics. So that minimum intensity is what is called this threshold of hearing. Hard and fast value, because every human being has a unique physical form and shape and all that. But a statistical average accepted value is this for threshold of hearing, 1 picowatt per meter square. Whereas on the other hand, there is also something called threshold of pain, which is a statistical average for the loudness, such that when intensity is more than this, it can cause physical damage, or definitely it can cause physical pain in the eardrum. So that's like the upper limit. You don't want to hear sound continuously, which is of more than this. So that is why factory workers or people who work in airports, etc., have to wear ear protection equipment, because prolonged exposure to loud sounds, which are more than this threshold of pain, will definitely cause them not only pain, but eventual permanent damage to hearing also. Okay. So that these are two other things that you should know. Okay. So you can just note down the values if required, but nothing more here. It's like general knowledge. Now, the next thing, there is something called decibel scale of intensity, or in short, it is called dBs. Decibel scale of intensity. So it is just a different mathematical way of expressing the intensity using a logarithmic system. So it is a logarithmic system or scale for measurement of intensity. Okay. So the intensity of any sound in decibels is given by this simple formula. Just a number 10 multiplied by log to the base 10 of the intensity of that sound in watt per meter square divided by threshold of hearing. I naught is that 10 raised power minus 12 watt per meter square, which is basically the threshold of hearing. Okay. So for example, if the intensity of a sound is, let's say, 2 into 10 raised power minus 8 watts per meter square. Now we want to express this in decibels. So we'll just apply the formula. This intensity in decibels is equal to 10 log 2 into 10 raised power minus 8 divided by 10 raised power minus 12. So that is 10 log 2 into 10 raised power 4. So now we can sort of start using the formula of log.
12 point something.
So log 2 is about 0.3.
Yes.
And log 10 is 1. So this will be about 43 decibels.
40. Yes.
Okay. So this intensity in decibels will become, so basically we can say that 2 into 10 raised power minus 8 watt per meter square converted to decibels is 43 decibels. So this is the formula, and this is the simple application of the formula. Now, there are a couple of things related to this that we should know. So write this down first quickly, and then we'll discuss about that. Okay, done now. Okay.
Yes.
Now, one simple thing that we should remember, which is very useful while doing calculations, is something that electrical engineers and sound engineers call the 3 dB rule. Okay. That if one intensity in watt per meter square is double of a certain other intensity in watt per meter square, okay, then this I2 in decibels is equal to I1 in decibels plus 3 dB. Okay, now this is very simple to understand because I1 in decibels is 10 log I1 divided by I0 in watt per meter square. Okay, I2 in decibels is 10 log I2 by I0 in watt per meter square. So if you subtract these two equations, I2 in decibels minus I1 in decibels is equal to 10 log I2 by I0 minus log I1 by I0, and that is 10 log I2 by I1. So that is 10 log 2. So that is 3. So I2 in decibels minus I1 in decibels will be 3 dB, provided the ratio of I2 and I1 in watts per meter square is double. Okay, so for example, we had just seen that 2 into 10 raised power minus 8 watt per meter square corresponded to 43 decibels. So this simply means that 1 into 10 raised power minus 8 watt per meter square is 40 decibels. If 4 into 10 raised power minus 8 watt per meter square is 46 decibels. 8 into 10 raised power minus 8 watt per meter square is 49 decibels. Is what it means. So that is the difference between something in a logarithmic scale and something in a decimal scale. When we convert from decimal to logarithmic, you have this property.
Sir, done.
Okay. Okay, now next up, let's see another very important relation. When we have a point source of sound, or basically a source of sound whose own dimension is negligible compared to the distance that we are taking from it. So if that point source is emitting a power P, then at a distance R from it, the intensity becomes proportional to P divided by R square. Okay. In a perfect world where there's no absorption and all that, it would be equal to that power divided by 4 pi R square, because that power is distributed uniformly on a spherical surface of radius R. But that doesn't happen because there will be some reflecting surfaces nearby. There will at least be a floor that is reflecting and all that. But nonetheless, the intensity is directly proportional to the power of the source and inversely proportional to square of the distance. So that means that when we double the distance, okay, the intensity becomes 1/4. Okay, so that means there is a 6 dB drop, okay, in decibel scale. So this is something important. So for example, if the intensity is, let's say, okay, 80 decibels at a distance of 20 meters from a source. Now we want to find the intensity in decibels at R equal to 10 meters and R equal to 40 meters. So you should not have to think twice about this and apply this formula and all this. You should just remember that if I, for example, double the distance, the intensity has become 1/4. So at 40 meters, the intensity will be whatever it was in decibels at 20 meters minus 6 dB.
Yes, sir. 7.
Okay. Yeah. So here it will become how much? 74 decibels. Whereas at 10 meters,
86.
it will become 86. Okay. So intensity at 10 meters will be intensity at 20 meters plus 6 dB. Should become 86 decibels. Okay, so that kind of concept. So this is again something we should remember. Okay. Intensity versus distance. Okay, so that is about all this. Okay. Now let's quickly move on towards superposition of sound waves, which will not take any time because we have already done superposition of transverse waves, but few differences we'll have to quickly understand in how to handle questions. So So as usual, the first type of superposition we'll talk about is interference. Okay. Now here, there's going to be slight difference in definition. If you remember, for transverse waves, what was the condition for interference? Superposing waves of same frequency and propagating in same direction, right?
Yes, sir.
Okay, but here there is no directional condition. It's just that if sound waves, that is multiple sound waves of identical frequency superimpose, they can be coming from different directions also. It's no problem. Okay. Then there is the phenomena of interference. So for example, we can have one sound source S1, which is creating a sound of frequency F, and another source S2, which is creating a sound of frequency F. And there is a detector somewhere here. So the waves reaching from this source are traveling, let's say, a distance x1. The waves reaching from this source are traveling a distance x2. But as long as they have same frequency, they'll have same wavelength also, because V is same. So now we always represent sound in terms of pressure, because that is the way the neurosensory perception of sound also happens. It's always in terms of pressure. It's easier to understand how the phenomena of sound works. So from source S1, if the pressure variation is given by some, let's say, PA, where P is the amplitude of that source, okay, sine omega t minus kx, and from, so this will be kx1 because it's traveled a distance x1, and from source S2 it is some new amplitude, but same omega, same k, different distance, and let's say the sources have some phase difference phi naught. Okay, then the resultant wave will have a pressure variation given by the superposition of these two. Okay, so now we can just copy paste the maths that we have seen earlier, and we can understand that this will create some net pressure amplitude into sine omega t plus, I'll just write it as some phase constant. We will understand what that phase constant is. Okay. So here, that net pressure amplitude, this will be the phasor resultant, okay, of PA and PB. So it will be that kind of thing, that if this is our PA, this is our PB, and this represents the phase difference delta phi, then this third side here represents the net pressure amplitude, and this term here represents epsilon. Okay, so more important is that net pressure amplitude. So you can see here, first of all, from these two, phase difference delta phi will become this whole term minus this whole term. So it will become k into x1 minus x2 plus phi naught in this case. Okay, so it is basically again that 2 pi by lambda into path difference plus the initial phase difference phi naught here. Okay, and our net pressure amplitude is given by, formula wise, it's given by the triangle law type of formula. So nothing extraordinary over here. But because now there is no constraint that both waves have to be traveling along the same straight line, there are a lot many different variations of questions that come into play. So we'll discuss one or two.
Sir,
Yes.
sir, can you again explain interference? I had some network issues.
Okay, so interference by definition is very simple. It is the phenomena that occurs when there is superposition of two or more, that is multiple sound waves of identical frequency. That's it. Okay. So in the example below, I've shown you that there are two sources S1 and S2, which are of same frequency f. So omega is equal to 2 pi f for both of them. Okay, so k will be equal to omega by v, where v is the common speed through air. So the sound is propagating through the same air. So they will have the same wavelength also, no?
Yes, sir.
So this k and omega term are same for both the sources. Okay, because the frequency are same. But now this one is traveling through a distance x1 up to the detector, and this one is traveling through a distance x2. And let's say the sources also had a phase difference of phi naught. Okay, that might be because there is some delay in the start of P1 compared to P2, etc., whatever. So what will happen is when we superimpose these two, that is when we add P1 and P2, we can see the phase difference between these two terms becomes this. You have to just subtract the argument of P2 with respect to the argument of P1. So the omega t term cancels out and we get k into x1 minus x2 plus phi naught. So that becomes the net phase difference between the two waves. Understood, no?
Yes, sir.
So now once we know that net phase difference, the resultant amplitude just depends on that. No? It depends on the phase difference delta phi and the individual amplitudes PA and PB. So you can just remember it in terms of this phasor diagram or in terms of the formula related to that, which is the same as your vector triangle law.
Yes, sir.
Okay, so now one of the common types of phenomena related to this is something like this. If we have a source of sound here and a detector over here, okay, and this distance between them is known, this distance is d. Now there is a reflecting wall. Okay, so what will happen is that the detector will receive two waves of sound. One is the direct and one will be the reflected. Okay, so I'm not making the best diagram here, but so if this happens, now we want to find, okay, so suppose we are given the value of d and small d and we are given the value of this length. Okay, so we want to find and we are given frequency. So suppose f is, let's say, 100 hertz and speed of sound is, suppose we are taking an easy value, 300 meters per second. Okay, now d is, let's say, 40 meters and L is equal to 15 meters. So we have to find path difference between direct and reflected waves. And from that, we have to find phase difference between the direct and reflected waves. Okay, so just try this out. So here you'll use the concept that sound is a wave just like light. And so reflection from a plane surface will follow the same principle as reflection of light from a plane mirror. That angle of incidence will be equal to angle of reflection. So using that, you will find the path difference.
Sir, during the case of interference, the sound cancels each other, right? Sir, during the case of interference, the sounds cancel each other.
Can cancel if there is destructive interference. So for that, the phase difference has to be an odd multiple of pi. But there can also be constructive interference, in which case you will hear a much louder sound.
Yes, sir.
So both the situations are possible. And of course, everything in between. It can be in between constructive and destructive. So neither they are trying to cancel, nor they are trying to reinforce, but there is some resultant intensity that you're getting, right?
Yes, sir.
Okay.
Sir, and if like two sound waves are traveling from opposite direction, one of them is of a larger frequency. So will interference occur or?
No, if the frequency is different, better, then the phenomena will not be interference. Okay, but then we will see in sound next that there is another phenomena called beats that occurs when slightly different frequencies, like suppose one is 300 hertz and the other is 305 hertz or 302 hertz, then we hear a phenomena which is called beats, where the resultant sound's intensity has a slight modulation.
Yes, sir.
So it's like the amplitude is not constant with respect to time. The amplitude or intensity varies. It modulates a little bit with respect to time. So it periodically varies with time. But in the case of interference, the condition necessary is that the intensity should be uniform. So that means that the frequency should be identical. The phase difference should be constant. So the omegas can't be different.
Yes, sir.
Okay, just work this out, please.
So then,
Okay, people. So let's understand this. So you can see that the direct path, so we can take this as the first path, x1. So
yeah,
x1 is equal to d, which is given to us as 40 meters. But x2 is basically, if we take this to be z and then this to be z. Okay. So you can apply Pythagoras theorem and all. We can see that. So z will be square root of d by 2 whole square plus l square. Okay, so that is
20.
25. No. So this
Yes.
is becoming 50 meters.
Yes.
Okay. So our path difference is 10 meters. So
Yes.
that's the answer to the first part. Okay. Now we can also see that from this and this, we can see what is our wavelength.
3.
3 meters, right? So our path difference is 10 by 3 times lambda. Okay. So that is basically how much. So our phase difference, delta phi, because of this will be, okay, which we can write as, now 10 we can split as like this. Okay. So it is 6 pi plus 2 pi by 3. Okay. Now 6 pi is as good as 0. So it's basically 2 pi by 3. So our phase difference is equivalent to 2 pi by 3. Our actual phase difference is this much, but it is equivalent to this much. Okay. So now, for example, if I said that, suppose the intensity of direct sound is, let's say, 90 decibels. Okay. And reflected sound is, let's say, 60 decibel, because a lot of absorption is happening. Okay. Then find the net intensity in decibels. Okay. So this is where a little bit of extra understanding is required. So what we had seen earlier is that the resultant amplitude is given by this. This, okay. So now we can see that the resultant intensity is proportional to P net square. And the individual intensities are proportional to the individual amplitude squares. But here we are talking about intensity in watt per meter square, not in decibels. So we'll come back to in this. Okay. So this formula that we have written for net amplitude can now be converted to a formula for net intensity. If we square this, we can say that P net square is equal to PA square plus PB square plus 2PA PB cos delta phi. So we have the net intensity is equal to this. So this becomes an additional very important formula, not only in sound, but later when we see wave optics also, you'll see that this formula is quite important. Okay. But here also intensity is in watts per meter square. Okay. So now think how we can use the data that I've given above to get the net intensity in decibels. This is like a third part of this question. We've already got this in the second part, that the phase difference is 2 pi by 3. Oh, that's 120 degrees. Okay, so cos delta phi is minus half. But now how we'll use this formula to get the net intensity in decibels, where IA and IB are not given in watts per meter square, but are given in decibels. Okay, so first of all, what we'll have to do is we'll have to understand the relationship between this I1 and I2 in
2 raised to 10.
watts per meter square. What is the relationship? Very good. Okay, so I1 is 90 decibels and I2 is 60 decibels. So there's a huge difference actually between them.
Yes.
So we can see that in decibels is 30 decibels. So that means 10 log I1 by I2 in watt per meter square, that is equal to 30. Okay, that means log I1 by I2 is equal to 3. That means I1 by I2 is 10 raised by 3. Isn't it? Okay. So that means whatever I1 is in watts per meter square, it is 1000 times I2 in watt per meter square. Okay. And in fact,
Shouldn't it be like precisely 1024 or something?
No, that is you're confusing with binary beta. This is base 10, no?
Oh, yes.
That you're confusing with binary algebra, kilo by 10. Okay. So now we can see that when I apply this formula, I net here will be I1 plus I2 plus 2 root I1 I2 cos delta phi. So we'll just write I2 as I1 by 1000. Okay. So this will be I1 plus I1 by 1000 plus 2 I1 by 10 root 10 ऐसा हो जाएगा 1000 in the denominator. Okay, into cos delta phi. Now cos delta phi is minus half. So it is I1 1 plus 0.01, sorry 001. Okay, minus ये कितना हो जाएगा? We can write this as root 10 by 100 now, and root 10 is approximately 0.32. So 0.032, sorry 0.0032, something like this. So this is our I net in watts per meter square. Okay, and we can always calculate I1 in watts per meter square because 10 log I1 by I0 is 90. That means I1 by I0 is 10 raised per 9. So I1 is 10 raised per minus 3 watts per meter square. Okay. That's why our I2 is 10 raised per minus 6 watts per meter square. Like this. Okay, so this is how to do the calculations in decibels or using decibel scale and intensity.
Sir,
Yes.
so what is the third term here? 0.031. Root 10 is 0.3 point something. Not 0.3.
Oh, my mistake. Root 10 is not 0.3.
3.2.
So it will be 0.032. 0.32, right?
Yes.
Okay, my mistake. So then this changes. Okay, and this also changes. So now this becomes how much?
It's the same. It's 0.031. 032.
Is correct now?
Yes.
Okay. So it becomes 0.96.
96.
Okay. 19 or something like this. Anyway, so something of the order like this. Okay. Now let's look at the other thing I was telling about, the phenomena of beats. So beats is a phenomena that occurs when we have sound waves coming from different sources of different frequencies, but such that the frequencies are quite close to each other. They are not equal, they are not identical, but they are close to each other. So this phenomena is called beats. The superposition of sounds of similar but non-identical frequencies. Okay, so suppose F2 is equal to F1 plus delta F, because F2 is larger than F1, suppose, then delta F should be less than equal to about 5 hertz for the beats to be audible. So I'll explain what this means, that what is audibility of beats. But first let's understand what beats itself is. So this phenomena results in a sound wave of oscillating or time varying amplitude, periodically time varying, amplitude, or that means intensity also. Okay. So I'm going to go over the explanation of this mathematically very fast through an example. I don't want to put too much time into this here. Suppose F1 is 500 hertz and the second one is creating a frequency of 502 hertz. Okay. And let's just say, for argument's sake, that the distance from S1, that is X1, and the distance from S2 is X2, they are such that K1 X1 is equal to K2 X2, because this will create, the source S1 will create a wave like this, okay, where omega1 is 2 pi f1 and k1 is v by omega1, and like that the second one will create a wave of a different frequency, therefore also of a different angular wave number. So omega2 is 2 pi f2 and k2 is v by omega, sorry, omega by v. My mistake. Okay, so suppose we take this situation, just for argument's sake. Okay, of course they need not be equal, but just to make the mathematical derivation a little easier here. Yeah, so I got disconnected for a moment. Anyway, so just to make the mathematics a little simpler, suppose we assume that k1 x1 is equal to k2 x2. Then the resultant sound that we hear, which is the sum of these two, and suppose they are not only equal, but they are also of the type 2 and pi. Or in fact, what we can do is, suppose we have selected the values of x1 and x2 such that both of them are this type. K1 x1 is even multiple of pi, and k2 x2 also happens to be an even multiple of pi. So we can drop those two terms. Okay. We'll just make the calculation easier to understand. So this term is, suppose, 2 and pi, and this term. So we just adjusted the distances from the source. This distance s1 and this distance x2. We have adjusted them in such a way that this is happening. So from this, what we'll realize is that now, if you look at the two waves, you have a phase difference which is time dependent. It is omega1 minus omega2 into t plus k2 x2 minus k1 x1. Okay, so this is a constant term, but this is now time dependent. So because the phase difference is time dependent, you can visualize the Phasor diagram. What will happen is that the amplitude will be riding on a phase difference which depends on time. This phase difference is basically like this, plus some constant. That means this phase difference is changing with time like this. So this whole phasor is going like this. So you can see that the net amplitude will therefore be varying with time. So phase difference varies with time periodically at a frequency which we call the beat frequency, which is the difference of these two frequencies, f1 minus f2. I'm writing it with a mod because whichever one might be larger. Okay. So that means the net amplitude, okay, that oscillates, that also varies periodically with time, with an amplitude which is with a frequency equal to what we call the beat frequency. Okay, so I'm just scrolling up a bit, note down the key points here. Then I'll explain the final formula and the result that we'll get from this also. Okay, so let's now understand. So without getting into the mathematics here, we will look at the derivation and all of this mathematically later when we study this chapter for IIT also. Okay, here we can just understand it physically like this. Now, just imagine, for example, our case where this is, so the beat frequency for this, which is the difference of these two frequencies in magnitude, is 2 hertz. Okay. So our phase difference here, delta phi, would be, omega 1 minus omega 2 into t plus some constant. And this constant term is basically what? This constant term is k1 x1 minus k2 x2, which I can anyway drop because I've taken them as 2n pi and 2m pi. But more importantly, this phase difference is 4 pi t, in this case with a negative sign. But so you can see that at t equal to 0 is looking like this. Okay, but at t equal to, for example, 1/4 of a second, okay, that is 0.25 seconds, it look like this. Okay, then again at t equal to 0.5 seconds, look like this. Then because this is continuously going round like this. Okay, so you can see that the net amplitude at any point of time is going to be this chord of a circle where this is continuously rotating like this. So the net amplitude will vary between its maximum net amplitude will vary between its maxima of 2 p naught and its minima of 0 at a frequency equal to, in this case, 2 hertz. When I've taken f1 as so, that means that the sound that we'll hear, the resultant sound that we'll hear, will have a time varying intensity or a time varying amplitude. So what we will hear is a pressure variation with respect to time, which looks something like this. This cycle will be approximately 2 milliseconds, but this cycle this will be like half a second. Okay, so there is variation of loudness. So if we compare this with P1, which was P naught sine omega 1t, that was a uniformly loud pressure variation. So the amplitude was uniform. So F1 was 500 hertz. So this was 2 milliseconds. If we saw P2 individually, so F2 is 502 hertz. So that would also look very similar. Slightly different frequency, but hardly noticeable. But when we see P1 plus P2 together, we get the phenomena of beats. That is, the amplitude varies with time periodically. At this kind of frequency. Okay, so this is the related phenomena when there is superposition of waves of different frequencies. But for the beats to be audible, the beat frequency should be less than about 5 hertz. Otherwise, the variation in loudness happens so fast that instead of hearing it as a variation, we sort of hear the average loudness. So we will not be, so the beats will not be audible. So that's what I meant by saying that for the beats to be audible, the beat frequency should be less than about 5 hertz, less than equal to 5 hertz, so that we are able to clearly discern that the loudness of the sound is increasing and decreasing periodically. Otherwise, that variation is so fast that our hearing system is not able to process it. It just processes an average loudness.
So, so
Okay, so this is the phenomena of beats, people. Okay. And then one final thing related to sound, which again you would have heard about, is Doppler's effect. Anyone heard of this term, Doppler's effect?
yes,
Can you tell me what is Doppler's effect when it occurs?
change in the frequency
Because of
of the moving.
Yes, very good. Relative motion. So
Yes.
all of us have experienced it in our everyday lives. Like when you are standing on the road and a vehicle goes past you at a high speed, and while it's moving, it's also blaring its horn. You can distinctly hear the frequency of the horn changing very rapidly as it goes past you. Because as it goes past you, its motion changes from approach to separation.
Yes.
So while a source is approaching an observer, the frequency will appear to be higher than the actual frequency emitted by the source. Whereas when the source starts receding or starts separating from the observer, then the frequency appears to become lower. So that rapid change in frequency occurs because of that. So Doppler's effect is the shift or change in frequency detected by an observer, okay, compared to the frequency emitted by the source. Compared to the frequency of sound emitted by a source. When there is relative motion. Between source and observer. So, for example, in case 1, we will see if the source of sound emitting a frequency f is moving towards a stationary detector or observer. Okay, then the frequency of sound heard by the observer is given by the formula V upon V minus Vs into f, where over here V is the speed of sound in air. Okay, whereas Vs is the velocity of approach of the source towards the observer. But similarly, if the source is moving in such a way that it's receding or moving away from the observer to stationary, now the frequency becomes less. So now Ps is the velocity of separation of source from observer. Both of these, f is the frequency of sound generated by the source. Whereas f prime is the frequency heard by the observer or detected by the observer. Okay, so in this case, we'll see that f prime is greater than f. In this case, we'll see f prime becomes less than f. Yes.
I had a question from the previous year question paper.
Yeah, tell me.
I send it to you in WhatsApp.
Yeah. Okay. Have you sent it just now again, beta?
Yes, sir. One.
Ah.
So one. Yes, sir.
Okay. Just going through it. Yeah. So in this, what is happening? A spacecraft which is moving with a speed u relative to the Earth in a direction in the x-axis enters the gravitational field of a much more massive planet, which is moving with a speed 3u in the negative x direction. The spacecraft exits following the trajectory which is shown. Okay, the spacecraft is moving at u relative to the Earth, the positive x direction. Planet is moving at 3u. That also we'll have to assume is with respect to the Earth. The speed of the spacecraft with respect to Earth a long time after it has escaped the planet's gravity is given by okay. So now what we can do in this type of question is that we can understand that if this is a positive x direction, then the initial speed, the speed of the spacecraft with respect to Earth
Yes.
was plus u I cap, right?
Yes.
And the speed of the planet with respect to the Earth, the velocity of the planet was minus 3u I cap. So from
Yes.
this, what we can say of the velocity of the spacecraft with respect to the planet become the difference of these two? Plus
Yes.
4u I cap.
Yes.
Okay. Now basically see what happens. So when the planet, when the spacecraft makes that complete U-turn kind of thing, okay, and it escapes the gravitational field of the planet. So what's happening? Again, its gravitational potential energy with respect to the planet is tending to zero. Okay.
Yes.
So its kinetic energy in the planet's frame has to be same as what it was before. So it has to have opposite direction, but same magnitude of velocity with respect to the planet. So that is minus 4u I cap. Okay. Now you understood. Now, so now I know this thing. Okay. Now from this, I also know that the velocity of Earth with respect to the planet is what? It is plus 3u I cap.
Yes.
Okay. So now what will be the velocity of the spacecraft with respect to the with respect to Earth in the final situation? It will be velocity of this spacecraft with respect to planet minus velocity of Earth with respect to the planet.
Yes.
Right? So it will become minus 7u I cap.
Okay.
So by the time the spacecraft has completed that maneuver, okay, and it's now moving away from the planet, escapes its gravitational field. In the Earth's frame, its velocity was this when it was approaching. The Earth's frame, its velocity is now this after it is separating. Okay, whereas in the planet's frame, this and this are equal and opposite. Okay, but is this concept clear?
Yes.
Okay. Okay, so we are mostly done with sound. Okay. Yeah, just one more thing. I have to do Doppler's effect. I got sidetracked just a moment. We'll just complete Doppler's effect. So then that we are done with sound. So the third thing in Doppler's effect, we saw when the source was moving towards or away from. We can also have a situation where the source is stationary. Okay, and the observer is moving towards the source. So in this case, the frequency heard by the observer becomes this formula, V plus VO upon V into F. Whereas, so again, F prime is greater than F because the observer is moving towards the source. Whereas if the observer is receding from the source with a separation velocity of VO, then it becomes V minus VO on V times F. So F prime becomes less than F. Okay. Now we can have a combination concept like this. That suppose something like this is happening. That the source is also moving towards the observer. And the observer is also moving towards the source. And the source, as it is moving, it is emitting sound of frequency F. Then the frequency observed here will become V plus VO upon V minus VS, because both are approach velocities.
So can we just like find the relative velocity of one of them and then?
No, the problem is why we can't do that is if we go into the frame of one, then in that frame we'll have to adjust the velocity of sound also.
Oh, okay.
You understanding now? So here it's assumed that sound is traveling at a speed V with respect to the medium around which is stationary. Now, if I get into the observer's frame or the source's frame, I can apply the formula, but I'll have to adjust the value of V, the speed of sound. I'll have to take the speed of sound relative to the observer.
Okay, understood.
And then when I do that, I'll come back to this formula only. Okay, so
yes, sir.
Okay. So now, for example, if I have a situation where the source is moving towards the observer, but the observer is moving away. So one will pick up from this and the other will pick up from the earlier where the source was moving towards the observer. So F prime will become V minus VO because this is a separation, but V plus VS in the denominator because it is an approach. So this kind of formula will have. Okay, so this is the application of Doppler's effect. Okay, so with these formulae, you should be able to apply the question, applying the questions. Okay, sometimes we make use of binomial approximation while doing calculations because typically, you know, V is like 340 meters per second or more than 300, and VS and VO might be very small, like 4 or 5 meters per second. So that calculation sometimes becomes a little tricky. So we can make use of binomial approximation to bring the denominator upstairs in the numerator and do some kind of approximation. So we'll maybe pick up some questions in the next lecture from KVPY question banks and discuss about that. Okay. You people have some KVPY question banks, right, which were given to you?
Yes, sir.
Yeah. Okay. So next lecture onwards, let's start working.
Not the question banks, but the previous year question papers.
Yeah. So that only. I mean, previous year question papers. So next lecture onwards, let's start working out some questions systematically from that year wise or something. Okay.
Yes.
Okay, so that's it for today's session, people. Wish you all the best. Okay. And hope to see most of you very soon in offline sessions, doubt sessions, etc. coming up next week.
Are you going to come to Andheri?
Andheri, not immediately, better. Let's see, because I'm more designated in this Navi Mumbai Thane area. But some point of time, definitely I'll come.
Okay.
Okay. Okay. Good night, people. Wish you all the best.
Thank you, sir.
Bye.
Thank you, sir. Bye, sir.